Hello students, let us begin Module 6. This corresponds to the latter half of Chapter 3 of our textbook. In the previous module, we talked about vector spaces, so let's begin with a little bit of a reminder. What is a vector space? A vector space is a non-empty set with well-defined addition and scalar multiplication, which satisfy these algebraic rules. By the way, here, scalar means the set of real numbers unless specified otherwise. We went through some non-trivial examples of vector spaces, and the simplest and also the most typical one being the n tuple of real numbers, Rn. The next topic we considered was the subspace. A non-empty subset of a vector space V is called a subspace if it is a vector space on its own with respect to the same algebraic operations. So the W must have well-defined addition or close on the addition and well-defined scalar multiplication or close on the scalar multiplication. It turns out that these two are enough because all the members of W, being the member of V as well, must automatically satisfy all these rules. So therefore, no reason to check all the 8 rules. All you have to do are these two. By the way, I added one more, which is not really necessary, but it was useful, especially when you have to disprove a certain set is a vector space. In that case, typically you just look for 0, and whether 0 vector is in there, then nope, it's not a subspace. If it is in there, then of course, chance is it's going to be vector space, so you'll have to try to prove it. That can be a little bit harder. So whatever problem, if you have a subspace problem, begin with the 0 vector. That was my suggestion. I hope everybody remembers. Okay, I spent a bit too much time on the review. Let's go to the next topic. An equivalent way to express a subspace or equivalent condition for subspace is just this one-liner, close on the linear combination. So well-defined addition and well-defined scalar multiplication, combine them together, we get well-defined linear combination. Now this kind of expression is called linear combination, but those are for just 2 vectors. If you have a lot more vectors, n vectors, this kind of thing is called linear combination. Now, what further properties do we have about linear combination? There are 2 concepts that really stand out, and the final concept that combines those 2. One, generation. Let V be a vector space and V1, V2 all the way up to Vn be vectors in capital V. We say these vectors V1, V2 all the way up to Vn generate our vector space capital V if every element, every vector in capital V can be expressed as a linear combination of V1, V2 all the way up to Vn. Are we too verbose? Well, I don't blame you, it is verbose. So let's go to a little bit more formal definition here. At first, this formal expression may look harder than this verbose expression, but eventually you'll get to a point this is easier to understand. We have some stiff learning curve, yes, but that's what we are doing right now. But by the end of the semester, my goal is everybody see this one easier than that one. That's one of my goals. Anyway, let's come back. For arbitrary vector V from capital V, the vector space, there exist some real numbers x1, x2, all the way up to xn, such that the first vector V can be written as a linear combination x1 v1 plus x2 v2 plus all the way up to xn vn. It's the same as previous verbose expression in a lot more concise form. Now these numbers x1, x2, x3 all the way up to xn are called coordinates. And there's a bit of a problem. This coordinate may not be unique. And some textbook authors use the term coordinate only when they are unique, only when V1 through Vn are actually bases. but I usually use coordinate everywhere, and even if v1 through vn just generate, I'll still use the term coordinate. Next concept, linear independence. We say vectors v1, v2, all the way up to vn are linearly dependent if there is a non-trivial linear combination that add up to the zero vector. What do you mean by that? There is a certain coordinate x1, x2, xn, this expression, not all of them equal to 0, such that the linear combination x1, v1 plus x2, v2 plus all the way up to xn, vn are still zero vectors. If there is some redundancy, yes, certainly. For example, v1 and v2 are the same. In that case, we'll put 1 and -1. In that case, these will add up to 0, right? And then everything else just 0. It will be okay. This one is +1, that one's -1, so not all of them 0. That's an extreme example. But there are many cases that we have linear dependence. The key is, for some non-trivial expression, non-trivial coordinate expression of zero vector exists, this linear combination may turn out to be 0 for some non-zero coefficients x1, x2, all the way up to xn. Some of them may be 0, but not all of them 0. Now let's talk about linear independence. That says that's impossible. If there is a linear combination that leads to zero vector, or the coordinate expression of a zero vector, only if all those coefficients are 0. x1, x2, all the way up to xn, they're all 0. If so, we say these are linearly independent, otherwise linearly dependent. Now we talked about two very important concepts, generating and linear independence. Let's put those two together. A linearly independent family of vectors, v1, v2, all the way up to vn, linear independence to satisfy this, that also generate v, is called a basis. So yes, this condition, generating, and that condition put together, both of them, that's called a basis. And what were the examples of basis? Standard basis vector e1, e2, e3 of Rm. Those are typical examples. I hope everybody remembers. 1, 0, 0, 0, 0, 0, and then 0, 1, 0, 0, 0, 0, and then 0, 0, 1, and then 0, 0, 0, those kind of things. So linearly independent, yet also generating. By the way, if you have basis, then the coordinate expression is unique. In other words, arbitrary vector v from vector space capital V has a coordinate expression because it's a generator. You see, v1 through vn, it's a generator. So arbitrary vector should be generated by v1, v2, all the way up to vn. So this expression exists. Next, they're unique. If there's another expression, another coordinate expression, y1, y2, and so on, then they're the same as the first. And the proof, all you have to do is subtract one from the other. See, if I subtract one from the other, v minus v is equal to x1 minus y1 v1 plus dot 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 xn minus yn vn, and that's equal to 0 vector, right? Therefore all I minus yi is equal to 0. What does that mean? All xi is equal to yi. This doesn't look very good. Okay, all right. Actually, it's a one-liner proof. So we went through a lot of important concepts. Vector spaces, subspaces, okay, those are easy. A little bit harder one. Generators, linear independence, and then put those two together, basis. And extra knowledge, coordinate expression. Now, what we're going to do here now is, in order to have a generator, you'll have to have enough number of V's. You see, it'll turn out that there's no way we can generate three-dimensional vector space with just two vectors. Like, for example, if you have R3, then E1 and E2, 1, 0, 0, and 0, 1, 0, that's not enough. You need the third dimension, you see? So, in order to have a generator, you have to have enough number. Actually, the more the better. The more you have, the better chance. Now, linear independence is backward. If you have too many of V1, V2, Vn, there's a big chance that one or more of them can be expressed as the others, and they are unnecessary. So the less the better. The less the better chance these are linearly independent. It turns out that they merge at the basis. It'll turn out that the maximal number of linearly independent vectors is the same as the minimal number of generators. This number is called a dimension. So this is where we are headed. The maximal number of linearly independent vectors is the same as the minimal number of generators. It's not going to be easy to prove, but we'll do it. And once we do that, this number is called a dimension. And once we have dimension concept, we're going to open up some other things and talk about rank of linear maps and rank of matrices and things like those as well. But the primary goal right here is the dimension. And dimension concept is coming from, let me open those up again, combining these two, generating and then linear independent. And turns out it's the same as number of bases. Number of elements in the basis set. Number of basis vectors. And a little bit too confusing, without writing. So I'll stop here, and I'm going to talk about a little bit more precise treatments in the next video.